Welcome back everyone. In the last video we downloaded our data from the UCI machine learning repository. We downloaded the Wisconsin cancer data sets, and we basically tidy up our data, did some pre-processing, and we've arrived at this point now whereby we are ready to do our actual training itself. So let's get started with that. Start from scikit-learn. We're going to import neighbors, and we're going to import the k nearest neighbor classifier. Okay, so let's instantiate this k nearest neighbor, and the number of neighbors, we're going to set it at 5, and p is equal to 2. Now, do you remember what p is equal to 2 means? So let me just rejog your memory a little bit. So p equals to 2 here essentially will convert the Minkowski to Euclidean. Okay, so because you change it to 2, essentially what you have will be actually the Euclidean distance here. Right, having done that, so the metric is equal to Minkowski. All right, that's fine. So now we're going to fit our data, our X train, and also our Y train. All right, that ran pretty fast, and that's pretty typical of KNN, the actual learning process. It's very quick, but when you actually start working with large data set, that's when you have some issues, run into some issues, or it will slow down substantially. So from scikit-learn, now we need some the actual performance matrix now. So I'm going to import the cross predict, and also cross might not be using cross predict, but let's just put it in anyway. And from scikit-learn matrix, we're going to make use of the usual accuracy score, classification report, and finally the confusion matrix. Right, I'm going to copy a little function that I wrote previously, and from previous video you would have seen this before. Of course I can save this into a file and import it, but it's okay. I just sort of leave it here so that it's easier to actually visualize. So let's just print our score. Now the print score will be this one here. Okay, so the KNN is the name of the of the classifier for the k nearest neighbor that we did. The X train, Y train, X test, Y test, and the train is true. So this is still within the actual training set itself. So the accuracy score is 97%. Which is not too bad. There are some inaccuracy here, which is 7 and 8, as you can see. Why don't we actually now, let's run the actual test itself and see how it goes. And this is the actual average accuracy, because we've done, if I recall correctly, we have tenfold. So that's the tenfold. So it should actually come up pretty good. So it's 95%, so it's still within this 1 standard deviation range here. Overall, as you can see here, the precision score is pretty good, the recall is pretty good, the F1 score is pretty good. All in all, the performance has been pretty satisfactory. The reason is actually fairly straightforward. A couple of things. One is that your data, there's sufficient data compared to what we looked at in the past. That's the first thing. The second thing is that the classes are pretty even. Yes, there's 2 to 1, but it's pretty good as it is. You know, it could have been far worse, and because we have sufficient data, so it's not too bad. Right, I'm wondering now whether we can actually improve on that, and naturally that's what you will wonder as well. So let's do a grid search, and just to see if we can actually improve on that. So it's from scikit-learn model selection. Import the grid search function, and okay, so now the question now is that what is it that I can actually tune? So remember that you can actually run this, get the hyperparameters that you can tune. looking at this, there are quite a few things that you can do, but for now, I think what we will do is actually just use tune the number of neighbors. Okay, so the params that we're going to tune is n neighbors. So let's just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, right. So now what's left is just do the actual grid search yourself, not through search, grid search underscore CV. Let's equal to grid search CV, and it will put in our k nearest neighbor classifier, and the params is what we actually want to tune. We're going to use all of our calls so that we can actually get an answer right away. Verbose, let's go to 1, and let's just run this number of jobs. Seems to actually catch me every time. Alright, so that's instantiated, so let's just run the actual grid search now. Alright, mine finished in 5 seconds. It depends on your system. It actually varies from PC to PC depending on your computational power. Alright, so so let's just look at grid search, and we have a look at the best estimator. Okay, for the best estimator is this. It says n neighbors is 7, and also let's just run this and just look at the print score itself. And this time around, we're gonna fit in the grid search CV as our X-train. Why? No, let's not type this. Embarrassing for you to see me type wrongly. So just copy and paste that. X-train, Y-train, X-test, Y-test, training. This is the within the training. Okay, it comes at 97.25. Comparing to what we have here, it's 97.25, so there's no difference there. Average accuracy is 96.35. It's still running. So let's let that run in terms of the tenfold validation that it is doing. I'm just going to mute this, and when it finished training, I'll come back. Okay, the tenfold cross-validation is finished. So we're looking at the average accuracy is 96.35, and 181 is our standard deviation. 96.35, 162. Hey, it hasn't improved. Oh, that's funny. However, I guess this model, I guess you could call it a little bit more stable because we are using 7 neighbors instead of 5 as we were before. So let's have a look at the actual out of sample performance. I've changed the training to false. Now we're looking at the actual test score itself. 95.622, I don't think has improved from before. 95.62, 95.62. So it hasn't improved. So I guess we probably have to actually look at it from another angle, get more data to actually look at how it performs. So the best hyperparameters in this case is actually using 7 neighbors. Other things that you can actually pull out, just so that you can see this, is that you can actually pull out the mean train score. And this is the actual or the tenfold that is done. The other thing that you can actually pull up is the cross-validation results as well. These are the let's see which one. It actually has all the information, relative information that you want. Here is this. you have the split scores, you have the fit time, you have the score time, you have the test score. You can actually see the actual test score itself, and you can also see the actual standard deviation of both of these. In as much as the performance and the training score, this is what I printed just now. In as much as the test score itself, that's this. Yeah, so it's interesting because they are a rich source of information for you to actually extract a lot of these information for you to actually compare. With that, that's really the formalized or the formal training portion on using KNN on this project itself. We're not done yet because I'm just going to leave you with a simple assignment. You've learned a lot of different classification method. Without going into some of the more advanced ones, such as XGBoost, I'm going to give you an option of either using SVM, random forest, or XGBoost for those who are a little bit more adventurous and really want to actually make use of what they've learned. I'm going to give you these three, so I'd like you to pause the video and go and try it out with all these three and see which of these or how these three model works in comparison to KNN. Welcome back. How did that actually went? I hope you tried that out. At least one of the support vector, random forest, or XGBoost. I did all three just so that you can actually have a comparison, compare yours versus mine. This is the support vector machine with the code I'm just showing you. Just really very simple. It's just 5-line of codes. What you see here is the accuracy is 97.99. The accuracy score is 96.35 with standard deviation of 1994 support vector machine. If you look at the random forest, it's much better in terms of the accuracy, 99.82 versus 97. But the accuracy score is a little bit lower. The average is 95.79, 95.79, and the standard deviation is 164. It's a bit lower, but the actual accuracy score is a little bit lower as well. In fact, when you look at the accuracy score out of sample, it just seemed like random forest actually has overfitted to the training data. If we look at the XGBoost, 99.27 is very good. The 96 is the actual average accuracy itself. 96.16 is it's 96 is a bit lower than the support vector machine. 199 is the standard deviations versus 190. So all in all, support vector machine comes out to be the best amongst the lot. But how does support vector compare to the KNN? The KNN, if you're looking at the out of sample, is 95.62. In sample is 97.25, 97.25, 95.62, 97.25, 95.62. So support vector machine indeed has come out at being the best amongst the three. But don't forget that we have not actually tuned any of these. Notice that when you take a look at the support vector machine, all I use is RBF. I did not set anything else. The same with the random forest, with the exception of maybe the random state is equal to 42. And also the XGBoost, I also did not actually set any parameters as well. So all these can be tuned. This can be an exercise for you to spend some time, figure out the tuning itself, and see if you can actually improve on those scores further. But for now, this is really the end of this portion. And we've covered everything with regards to KNN to actually get you started. If you want to read more and want to learn more about KNN, do feel free to use the scikit-learn library. There are a lot of good documentations, and don't forget too that I have actually provided the actual link itself for you to actually read as well under the KNN. So over here, these are some of the links that you can actually go and read up more. For now, this is me signing off. Thank you for watching, and that's really the end of this section. Thank you for paying attention, and look forward to seeing you in the next lesson.